In this video, I'm going to be working more examples using trigonometric functions. So far we've dealt with the first quadrant. So what happens when we have a vector that's pointing into the second quadrant? If we look at our coordinate axes, we can see here that this is the negative x direction and we're still pointing in the positive y direction. Now, typically, if I would be solving for values in quadrant 2, I would still work with all positive values for our components. What do I mean by that? Well, the actual value here for this x component of this vector would be negative. We can see that it's pointing in the negative x direction. And the y component in this case is positive. If I'm working with my trig functions, I don't really have to worry about the signs of the components until I'm ready to write my final answer. And I can determine the signs of the functions by just looking at the graph. So let's solve a little problem here. Let's say we're given this component. Let's call this d sub x. This is d vector. And let's find the magnitude of d vector, and we're going to be given d sub x as -5 meters. Okay, well, I don't have any information about d sub y, but I'm given d sub x as -5 meters. So I write my mnemonic, so ka toa, and I have the adjacent side. I want to find this hypotenuse. So then what is the cosine function? And we are going to need an angle, so let's call this 45 degrees. So the cosine of 45 degrees is equal to the adjacent over the hypotenuse. We're given the adjacent side as -5 meters, and the hypotenuse we're just calling d, which is the magnitude of d vector. I'm going to equate the left and the right-hand side since they're equal in this triple equality. So let me rewrite that just to be clear. The cosine of 45 degrees equals -5 meters divided by d. Now, the only unknown is d, so I need to use some algebra to get d by itself. So if I multiply both sides by d, then I have d cosine 45 degrees equals -5. And then the cosine of 45 degrees is just a number, so I can divide both sides by cosine of 45 degrees. I'll divide the right-hand side by the cosine of 45 degrees. And I'm left with d equals -5 times the cosine of 45 degrees. When I put this in my calculator, I don't need to put the negative sign in if I don't want to. I can either put it in there or I can leave it out. As long as if I leave it out at the end, I need to look at my graph and see which quadrant I'm in and say, okay, well, d sub x is clearly negative because it's pointing in the negative x direction. If I put it into my calculator, that's fine as well. So d then, I need to put this in my calculator. And be sure that you are in degree mode, not radian mode. And it's -5 divided by the cosine of 45 degrees. And the value I get, d, is equal to -7.07, rounding to 2 decimal places. If I leave out the negative sign, then it's just positive 7.07. So again, if you don't put your negative sign in the calculator, you still have to look at quadrant 2 and determine what is the sign of your vector. And just to make that clear, once again, d is -5 divided by the cosine of 45 degrees. If you put the cosine of 45 degrees into your calculator, you'll find that that's a positive number. Its exact value is the square root of 2 divided by 2. So you have a negative number divided by a positive number. This has to be negative. And hopefully that makes sense to you. D is really the rise over the run. It's just the slope. So the rise is positive, dy, and the run is negative, dx. When you divide a positive number by a negative number, the end result is going to be negative. Okay, so let's do another problem. So let's say I have my coordinate axis here. And my hypotenuse is now in quadrant 4. So this is quadrant 4. So this would be, let's call this Vy. Let's call this Vx. And this is my V vector. Okay, now, let's say that we're given Vx as being equal to 2 meters per second. And then let's say that we're given Vy as being equal to -3 meters per second. It's negative because in this fourth quadrant, you can see we're pointing, Vy is pointing in the negative y direction. Vx is still pointing in the positive x direction. So what I want to find is this angle that the v vector makes with respect to the horizontal. What is that angle? So I write out my mnemonic here. I have again, so TOA. And I'm given my opposite side, which is Vy, and I'm given my adjacent side, which is Vx. So I'm wanting to find theta. Theta is what I'm looking for. So to find theta, I'm going to have to use an inverse trigonometric function. And I have all the information for the tangent function. So what I'm trying to do is I'm trying to solve for theta, okay? And I have my opposite side, I have my adjacent side, and that's all related to the tangent function. So I'm going to write then the definition of the tangent function. So the tangent of theta equals the opposite over the adjacent. The opposite side is v sub y. The adjacent side is v sub x. Now I can plug in my values for v sub y and v sub x. So v sub y is -3 meters per second. V sub x is 2 meters per second. So I see here, this is big equality. I'm going to equate the left-hand side with the right-hand side. And I need to now take the inverse tangent to get this theta here to pop out of the tangent function. So that looks like taking the inverse tangent of both sides, the inverse tangent of the tangent of theta. I took the inverse tangent of the left-hand side, so I have to take the inverse tangent of the right-hand side. So the inverse tangent of -3 meters per second over 2 meters per second. Simplifying this further, the inverse tangent then gets rid of our tangent, and we're left with theta equal to the inverse tangent of -3 meters per second divided by 2 meters per second. Now this I can put in my calculator. Okay, so I'm going to put in the inverse tangent of -3 over 2. And it's going to give me a negative angle in my calculator. Okay, so that gave me theta Rounding this angle to 2 decimal places, it is theta equals negative 56.31 degrees, and we're rounding that to 2 decimal places. So what does that mean? Positive angles go counterclockwise around the coordinate system. Negative angles go clockwise. So this is negative angles here. So negative 56.31, if this entire revolution is 360 degrees to make one revolution around a circle, then to find positive version equivalent of this angle, I can take 360 degrees minus 56.31. Where that comes from is simply I can either go in the counterclockwise or the clockwise direction. If I go in the counterclockwise direction, then I'm going to have a large positive angle to get me to the fourth quadrant. If I go in the negative direction, which is the clockwise direction, I'm going to have a smaller negative angle, which is the negative 56.31. So to find the positive equivalent of negative 56.31, I take 360 degrees minus 56.31. That gets me 303.69 degrees. 303.69 degrees. So this is the positive equivalent of negative 56.31. So just to show that here, negative 56 might take me down to about here. That was clockwise rotation. And then the normal counterclockwise rotation for a positive angle would actually come all the way around the coordinate axis, just like this, and it would meet it at that same spot, just from the opposite direction. And that would be, again, we'd have like a hypotenuse coming out like this. So either negative 56.31 degrees or 303.69 degrees, those are the same. So either one of those answers would work.